the session on reinforcement learning. My name is Elad Khazan. We have a really nice lineup of work here, and it's a pleasure to introduce our first speaker, Professor Shamka Kadeh from University of Washington, who will talk about his recent work in reinforcement learning. Please.
All right, thanks a lot. Thank you all for coming to the session. I'm Sham Kakade. There's been a lot of important applied work in reinforcement learning and controls with impressive empirical advances. And this has led to a growing sense of excitement from different communities to tackle these problems. In reinforcement learning, one of the tools we have up our sleeves are these policy gradient methods. And these methods are being increasingly used in controls problems. So why do we like these policy gradient methods? Well, they're simple to implement. They're model-free, so we can often run these methods where we don't have a model of the world, and we can directly try to improve our objective function. And another reason we like them is they're direct in that they're always improving our objective function, which in some ways might make them more robust to modeling errors. But at the end of the day, we actually want good policies, and the question is, will they actually converge to policies with good value? And that's the focus of this work. We're going to start looking at the most basic controls models, namely the linear quadratic regulator. And we're going to ask the question, do these local search-based methods get to the global optima? OK, so we'll start by reviewing the basic controls model. OK, so this is a model where we have states that are in d dimensions. We're going to take a control or an action. I'll use those terms interchangeably. Assume the actions are in dimension k. And the evolution of the world is going to be linear in both the current state x and the control we apply. Okay, and the dynamics are given by these two matrices A and B. We could have noise in the dynamics, but for now, assume they're deterministic. Okay, and what's our objective? Well, it's a quadratic cost function, so it's to minimize our cost over the infinite horizon, subject to the constraint that we follow the dynamics under this model. Okay, and let's assume we have some random starting state distribution. We'll come back to why we consider that later on. Okay, so is the problem clear? We have a linear dynamical system. We apply a control. We get a quadratic cost. And we proceed. And we're trying to find a controller, which is a mapping from states to actions, which solves this objective function. Okay, and we know that the optimal controller is one in which it's linear in the policy. Okay, so this is why these LQRs are nice in that they're an abstraction of linearizing a process and the optimal policy in the sense that the optimal control we take is a linear mapping in the state variable x. Okay. So let's review the solution concepts in this area. So suppose for a moment we knew the model of the world. Then we could find the optimal controller exactly. And there's two ways we can go about this. So one is to solve what are known as these Riccati equations. So this is some set of equations given in terms of this matrix A, the dynamics B, and B, and our cost Q and R. But we're trying to find a PSD matrix which satisfies this equation, and we can do this iteratively. Okay, and once we have that, we can plug that in to find this linear mapping. Okay, and this is something that we can basically find through iterative method. So we just run some fixed point method, it converges. Okay, another method that's exact is we can set things up as a semi-definite program, find this matrix P, and again, plug this in. Okay, and if we don't know the model case, often what's done is some kind of system identification followed by, in the system identification phase, we figure out the model. And once we have the model, we go back to one and plan using some exact solution concept. Again, there's definitely been a growing amount of work, even on this problem, in the machine learning community. Some work from Max I don't know how to pronounce his last name, and Ben Rex group, and then Elad Hazan and some of their group have been looking at solution concepts in this area. Okay, and in this work, we're asking a pretty basic question, which is, can we directly learn this linear mapping with a policy gradient method? Okay, and so what do I mean by that? So precisely, we have this cost function, C of k. So assume C of k is this quadratic cost. And suppose for a moment we knew the model of the world. Okay, so if we knew the model of the world, we can compute the gradients of our cost. And this is just gradient descent. Okay, so this is gradient descent to find the policy. Okay, and now a question is, does this converge to the optimal controller? Okay, so that's the setting, and this is basic because this is one of our bread and butter controls model, and more than just that, people actually use policy gradient methods in a lot of these linearized control problems. So there's a growing amount of work from various communities which actually use methods like this. Okay, so the first thing we point out is that this is not a convex optimization problem. Okay, it really is non-convex. I think in one dimension you can show it's convex. Maybe in two it's quasi-convex. But in 3 dimensions or larger, this is definitely not a convex optimization problem. Okay, so now we're asking the question, which is, will a gradient method actually converge in a non-convex optimization in these linear quadratic regulator models? Okay. So is the setting clear? Feel free to just yell if something isn't clear. OK. So the next dilemma we're going to look at is trying to understand the landscape of these problems and what might happen if we get stuck. Okay, so now a couple of definitions are in order. We're going to define sigma k to be the average of basically the covariance matrix of the states you visit. So xk is going to be the state you visit at time t. Okay, and this sigma k that's the expected value of the xk xt transpose matrix as you move around. Okay, so that's just a definition. Sigma 0, and that's as you move around under the policy k. Okay, and sigma 0, let's assume that's the covariance matrix of the start state distribution. Okay, so this lemma is actually pretty enlightening because what it says is, suppose we hit a point where a gradient is 0. Okay, so that's kind of where we'd expect gradient descent to get stuck at. It'll get stuck at a point where a gradient is tiny. Okay, so a basic question is, what does this imply about the quality of the solution? Okay, and in this exact setting, we can characterize what this implies, and it's one of two things. That if we're at a point where a gradient is 0, then either we're at an optimal policy, great, or it could be the case that this state visitation covariance matrix is degenerate. Okay, so and intuitively what's going on is everything looks optimal with respect to where you're currently visiting, but where you're visiting somehow isn't the entire space. So maybe if you moved in a slightly different direction, you might see something better. Okay, but and this is actually pretty relevant in practice as well, because we know there's this interplay between how good the policies we find and basically where they tend to visit. But note an immediate corollary now is, as long as the starting distribution is full rank, so that means we're forcing the system to start in different directions, that will imply that the state visitation frequencies are full rank, and that if you can find a stationary point where your gradient is 0, then you have a globally optimal policy. Okay, and I do want to point out that this really is an important practical issue, because a lot of thought is being given to how we start the local search space methods. And if you kind of start them in a flat region, one will get stuck. And granted, these are, this often occurs in richer settings, but we see this behavior even in the simplest of LQR models. Okay, so it isn't non-convex, but we have this nice property that as long as we visit kind of all the directions, then a 0 gradient implies a globally optimal policy. Okay. Questions? Feel free to yell a question if you have one. I think I have plenty of time. Okay, so what's our main result here? The main result, we're going to give the result in two parts. So the first part is, let's go ahead and assume we can get our gradients exactly. Okay, so we're running gradient descent. We're getting our gradients exactly. And the first result says that provided we set the parameters appropriately, if we run in an amount of time that's sort of logarithmic in our accuracy parameter, in a polynomial amount of time in these system parameters, we're going to find a policy whose cost is epsilon close to opt. Okay, so let's look at these dependencies for a moment. A bunch of them seem natural. Okay, so I need to clarify the notation, but these mu and okay, so I didn't define mu. Mu is the minimal eigenvalue of the start state distribution. All of these other values are spectral properties of these state matrices, like basically maximum minimal eigenvalues of things like your cost matrix, dependencies on the maximum eigenvalue of A and B. That should be expected because that governs like how big your states can get. Okay, so the one thing that's subtle here you might notice is this term in red at C of k0. Okay, so those of you who are pretty familiar with LQRs know that you might not be able to start at a stabilizing policy. So, and by that I mean, it's you could start at a place where you actually diverge. So this theorem is implicitly assuming that we can start at a stabilizing mapping. Now, at some level, this should be expected because it is a local search-based procedure. So if we start with infinite cost, it's hard to expect us to improve. Okay, but the important point here is that the dependence on the starting cost is only polynomial in C of k0. Okay, and then the rest we have reasonable dependencies more directly on the system parameters. Okay, and this is the case where we know the model. Okay, in the unknown model case, you can basically do what's known as zeroth order optimization. So if we don't know the model, what's the idea? We kind of inject a little noise into the system, and you can use rollouts to get stochastic estimates of your gradients. Okay, and even there, you can show that you can find an epsilon optimal policy in amount of time that's polynomial in the relevant quantities by appropriately injecting the noise. Okay, and the polynomial dependencies look pretty similar to that of the above, except the number of iterations it takes is now polynomial in 1 over epsilon. Okay, and the number of samples, on a related note, is polynomial in 1 over epsilon. Okay, so these are two results. The first one, I would argue, is actually like technically more important because once we understand the exact dynamics and how to do that, that immediately leads us to doing the analysis in the approximate case. Okay, so I'm just going to briefly mention the intuition for how this proof works, and I feel this lemma is actually pretty helpful more generally. Okay, and it's a lemma which says that we can relate how close we are to the optimal controller based on the size of the gradient. Okay, so what this lemma is saying is that if our gradient is small, we have to be close to the optimal policy. And those constants depend on problem-specific dependencies, and of course they depend on the starting distribution. Okay, and the reason this is powerful is it's one of the few tools we have in non-convex analysis to get to global optima, because you would hope gradient descent will get you at a place where your gradient is small, and a lemma like this actually says that if your gradient is small, you can't really be at a nasty SATA point. You actually have to have value close to that of optimal. Okay, now the reason that the proof is actually demanding is that this lemma isn't alone enough to get you there. What we really have to do is use this and understand how smooth our function is. And most of understanding the LQRs, the same with a lot of these recent results, is understanding how unstable they are, because the set of k with finite cost is actually not all k. It's actually a bounded set. Okay, so understanding how to analyze how smooth this function c of k is the entire set of technical hurdles in this proof. Okay, so this is the main idea of the proof. It's this really, this gradient domination lemma, which is pretty natural. Once we have that, there's just a lot of technical details for understanding smoothness. This is an interesting direction because it's actually related to stability questions. Okay, so the bottom lines is that, look, linear quadratic regulators are the bread and butters of our control models, and extremely natural question is, if we run one of these policy gradient methods on this non-convex optimization problem, can we get any handle on its behavior? And the short answer is yes. Not only do we understand its behavior under some mild restrictions, meaning that we just start the initial starting distribution to be spread out, you can show global convergence to the optimal controller in polynomial time. If you're interested in this direction, the paper does have some interesting extensions where we actually analyze both the natural policy gradient method and policy iteration and show some connections between these two methods. And there's lots of open questions in this area. And this is joint work with a number of terrific colleagues. This is Miriam Fazal, who's here. She's in EE, really with different backgrounds. Miriam knows convex analysis. So we're really combining a bunch of tools. Ron Gay is theoretical computer scientist. And Mehran Mesbahi, who's really in the controls community. Thank you. And questions?
Thanks, Sham. Any questions from the audience?
So I have a question.
Yes.
So it is interesting that the controllability Gramian doesn't appear in your bounds. So basically, the interaction between A and B seems that, at least in what you showed, does not appear. Do you have any comment on that?
Yes. It doesn't appear because I have this just dependence on C of K0. And all of that has been wrapped into C of K0. Because somehow we have to bound, gradient descent is moving in some ball, and it's going to depend on some stability properties, not just around the optima. It's going to depend on the stability properties around the entire cost ball that gradient descent lives in. And once we write C of K0 down, that hides all of that stuff. And I think this open question is really understanding how to, I suspect you're asking this because you're familiar with stability and how one sweats, and I think a lot of the difficulties is understanding how to relate these operator bounds to stability to sharpen up that dependence. Yeah, that's a great question.
I see one more question there.
Yes.
Yeah. So I was wondering if you could tell us the broader significance of the result in the context of hotter environments, because I'm not completely sure if knowing policy gradients can converge for LQR is particularly useful.
Yeah, okay, so the question is is this more broadly useful because we're looking at LQRs? Okay, so I'd argue that there's a sense in which LQRs are pretty important, at least in controls, because many of the practical schemes are based on trajectory optimization, and they're based on local linearizations. So what they'll often do is they'll do some local linearization of the world, and then actually run a finite horizon LQR on that. And then they'll actually find the optimal policy on this local linearization. And what this is arguing is that if we take that viewpoint, what this is arguing is that once you take the local linear model, you are going to find the optimal policy under this local linear model. So you aren't going to get stuck due to the fact you have a local linear approximation. What I would argue the significance is. So it's very much the same significance as using trajectory optimization, model predictive control when you're doing the local linear optimization.
Yeah, so why would you just not do model predictive control in the local linear and local quadratic costs?
Right. Okay. So I think this is the right question. So as we all know in RL, the hard part is dealing with function approximation, putting that into these methods, and we don't know how to make progress on that. And one question I am pretty interested in is how do we couple this with function approximation and understand how, say, modeling errors propagate into the system. And local search is one natural way to address it, but if we can't even understand local search in the most general framework, I think we have no hope in understanding how approximation errors seep into this. So that's basically my take on that. The real question is, once we start moving to approximation errors, how do we compare these things? And we have no handle on either of these two once there's modeling errors.
Okay.
Thank you.
So if I can I have time for asking you one small thing.
Sure.
And that is, I guess there is no acceleration here in your result. And is that because the Polyak original result doesn't work with accelerated gradient descent?
Yeah, I mean, that's what, it's really a non-convex optimization. Actually, that's a good question. So these gradient domination, technically, there's more structure on it. So it's a reasonable open question, which is, if we just take some non-convex optimization problem, assume it's gradient dominated, is there reason to believe there are faster optimization methods? And yeah, I mean, if I just tell you non-convex, like who knows? But with this additional structure, I don't know.
Okay, let's thank Sham again for an excellent talk. Our next speaker is Wei Zhang.
Okay. Hello, everyone. I'm very glad to present our recent work, Policy Optimization as Water State Gradient Flows. This is a joint work with Changyou Chen, Chunyuan Li, and Lawrence Curran. So let's start with the motivation of this work. Most work in reinforcement learning, such as proximal policy optimization and trust region policy optimization, employs stochastic policies, but the distributions are assumed Gaussian distribution. It restricted the expressive power of the policies, but the distributions encompass real problems. Recently, implicit distributions have been proposed where we don't have to make assumptions for the explicit assumptions for the form of the policy distribution. And we follow this line of work, and we propose to use Wasserstein gradient flows to do the policy optimization. Additionally, with the Wasserstein gradient flow, we can give better understanding of underlying mathematical principles of the policy optimization on the probability measure. Under specific circumstances, policy optimization becomes a convex problem in terms of the distribution matching, distribution optimization. Concurrently, we would like to propose the policy optimization with two settings. The first setting, we define the Wasserstein gradient flows on the parameter space, namely the posterior distribution of the parameters. And in the other setting, we define the Wasserstein gradient flows on the distribution space of the policy distribution. So our contributions are summarized as follows. And firstly, So we investigate the reinforcement learning from the perspective of how to better optimize the policy. And our proposed methods are interpreted as the Wasserstein gradient flows. However, original Wasserstein gradient flows are intractable, and we use the discrete Wasserstein gradient flows. Interesting, the Wasserstein gradient flows can naturally provide us a Wasserstein style truss region. And since we use implicit form of the distributions, we use the particles to approximate the distribution and propose a particle-based approximation for the Wasserstein gradient flows. And okay, sorry. So this is the contribution. This is the second of my contribution. Yeah. And the third contribution is a theoretically sound way to use the Wasserstein truss region. So next, I would like to introduce the background of Wasserstein gradient flows. And the Wasserstein gradient flows are defined on a Riemann geometry characterized by the second-order Wasserstein distance between two distributions. The evolution of the distributions, namely the Wasserstein gradient flow, are described by the partial differential equations. And the functional equation, the energy functional F, is defined as this way. And the energy functional is a mapping from a probability measure to a real value. And for the Eaton diffusion, the energy functional F is defined as follows. The KL divergence between the distributions we are learning and the optimal or target distributions. All the two settings of our reinforcement learning settings is similar to this form. And the P is the target policy, and the mu is the policy we want to learn. And the target policy is in the general energy-based form. So, however, the original Wasserstein gradient flows are intractable. So we want to solve it and by describe time flows. And we use the numerical solutions. After using the name of this numerical solution is the JKO scheme. After using the JKO scheme, solving the original Wasserstein gradient flows become an iterative optimization problem. There are two terms. The first term is the KL term. We want to minimize the KL divergence between the target policy distribution and the learned policy distribution. And by minimizing it, we will move the learned distribution towards the target distribution. And there is another term, the Wasserstein term. This is the second-order Wasserstein distance. It can work like as a Wasserstein truss region. So since we didn't make any assumption for the learned distribution mu, we use the particles to represent a distribution like this way. And the first term of the KL divergence can be updated by the Stein-Inversional gradient descent method. This is the previous work of NIPS 2016. And for the Wasserstein term, we propose a novel way to use particles to approximate the Wasserstein distance. The Wasserstein distance term is a complex force, and the Wasserstein truss region form this force is not pulling the consecutive policies together close. It has a complex force. When the particles are close to each other, it will push away a little of the consecutive policies. When the two policies are too far away from each other, we will pull them closer. So this is how the Wasserstein truss region works in the policy optimization. Now we are going to apply the Wasserstein gradient flows to two different settings. For the indirect policy learning, the policy is represented by a Bayesian neural network, and the Walther-Stein gradient flows are defined on the posterior of policy parameters. This is the same setting as the previous work, the Stein-versional policy gradient. Corresponding to maximizing the total reward target distribution is in the general energy form determined by the expected total reward. And empirically, we compare our proposed indirect policy learning with Walther-Stein gradient flow with the Stein-versional policy gradient. Our method is the green line is consistently better than its baseline. So we consider the direct policy learning setting. This is the same problem setting with the soft skill learning paper or last year's SML paper. DPWGFS is defined as this way, and the policy is also a general form or energy-based form. This is determined by the Q value. So in this way, we will simultaneously learning a stochastic state conditioned neural network L5 to approximate the implicit policy. The update is with the chain rule. The first gradient is use the Walther-Stein gradient flows to get the gradient. And the samples over the neural network parameters are using the standard backpropagation way. And the Q networks are updated using the Bellman error, the same as in the soft Q learning. So for the empirical evaluation, the direct policy learning, we compare with its corresponding baselines, the soft Q and soft actor critic. Also, we compare with the principal baselines, such as DDPG and TRPO. The experiments validate our proposed methods. So this is the summary of my work. We interpret policy optimization as Walther-Stein gradient flows, and we propose a particle-based approximation for Walther-Stein gradient flows. And we also propose a theoretical way to use trust region. Also, we define two types of Walther-Stein gradient flows for policy optimization. Okay, that's all. Thanks for your attending. Thank you.
Thank the speaker. So we move on to the next talk. And Yasuhiro Fujita will give this next talk.
Okay, good afternoon. My name is Yasuhiro. I work for Preferred Networks in Japan. I talk about a variance reduction technique for policy gradient methods with bounded actions. We address a mismatch between action space and policy, which is common when policy gradient methods are applied to continuous action problems. That is, the action space that the environment can accept is bounded, like an interval on the real line. But a policy we try to optimize has unbounded support, like a Gaussian distribution. When there is such a mismatch, actions sampled from a policy we denote by U may not fall inside the action space. We denote the lower bound of actions by alpha and the upper bound by beta. We need to clip actions outside the bounds to corresponding boundary values. alpha or beta, as this figure shows. Clipped actions we denote by U bar are then used by the environment to decide next state and reward. We apply policy gradient methods to optimize a policy for such an environment. This is usually done by computing a value like this, action value times the gradient of log PDF of a policy. Throughout this talk, we call this value PG for short. We need to use actions before clipping here so that this is an unbiased estimate of the gradient of the expected return of a policy. Empirically, it works well. But our question is, why not use the knowledge of the action space? Can't we improve it by using the knowledge of actions being clipped? Our answer to this question is yes. And here is how we can make use of the knowledge of actions being clipped. Suppose actions are scalar values for simplicity. We can derive a new estimator where the gradient of log PDF is replaced with this conditional expression. There are three cases, one for actions inside the action bounds and two for outside the bounds. For actions inside the bounds, it is completely the same as PG, the gradient of log PDF. For actions outside the bounds, we use the CDF of a policy denoted by capital Pi instead of PDF, and it is evaluated at a corresponding boundary value. We call this conditional estimator clipped action policy gradient, CAPG for short. For vector-valued actions, CAPG is similarly defined using the CDF of each action dimension as long as the distribution of action is conditionally independent given state. So what is good about CAPG? First, although it looks different, it has the same expected value as PG's. That means that CAPG is also unbiased. Second, CAPG's variance is actually lower than that of PG. That is, each element of the estimated gradient has lower variance than that of PG. This is good because we prefer lower variance when estimating gradients from a limited amount of samples. In this sense, we argue that CAPG is a better estimator than PG in this setting. We performed numerical experiments to validate these properties. Here, a Gaussian policy is parameterized with two parameters, theta mean and theta log STD. And we repeatedly estimated gradients using sampled actions by PG and CAPG separately. And the left figure shows the mean of estimated gradients with solid lines for theta mean and broken lines for theta log STD. And PG is represented by orange lines and CAPG by blue lines, but in this figure, they completely overlap. That means CAPG is actually unbiased. The center and right figure shows the standard deviation of the estimated gradients for different mean and variance of a policy as x-axis. Here, CAPG consistently achieved lower standard deviations than PG, as the theory suggests for both theta mean and theta log STD. We also performed our experiments with CPG. We use PPO and TRPO as base algorithms and replaced PG in these algorithms with CPG. The 10 Mujoko environments in OpenNIZIM were used for this evaluation. We found that for both PPO and TRPO, CPG either significantly outperformed PG or made no significant difference in average return throughout training for all the environments. These figures show average episode return throughout training. As in the left figure, we observed large improvements by CPG for some environments. And it made small but significant improvement as in the right figure for in some other environment. And there are also environments where CPG made almost no difference at all, or as in the left figure, or achieved slightly worse but not significant average returns as in the right figure. And here is a summary of this talk. When we tackle a problem with a bounded action space, and we optimize a policy with unbounded support, like Gaussian, we can use CPG and enjoy lower variance. Thank you.
Thank you. We do have time for one question from the audience, if there is any. Yep.
Hi, thanks for the talk. So if you're using this policy distribution for something like TRPO, how do you go about calculating like the KL divergence?
KL divergence is computed in the same way as the usual Gaussian policy. The only difference is the gradient computation.
So use the same formula as the Gaussian policy and just ignore the degenerate distribution pieces?
Yeah, the KL divergence is completely the same as the usual TRPO.
And same for entropy?
Yeah, same.
Okay, thank you.
Okay, let's thank the speaker again.
Sorry.
Okay. So our next speaker is Matthew Fellows, and he'll talk about Fourier policy gradients.
Hello, I'm Matthew Fellows, and on behalf of my collaborators from the University of Oxford, I'm here to present our paper, Fourier Policy Gradients, which is a new way of deriving policy gradient updates for reinforcement learning, allowing us to capture the low variance benefits of expected policy gradients in a broad range of settings by exploiting powerful Fourier analysis. So, firstly, let's have a little recap of policy gradient methods. In policy gradient methods, we seek to find an optimal policy by directly differentiating the reinforcement learning objective with respect to the policy parameters theta. Doing so yields the following gradient update, which consists of two integrals. We have one outer integral with respect to the state S, and we have an inner integral with respect to the actions. In our work, we are only concerned with the derivative of the inner integral over actions, which we write here as I theta. Like many policy gradient methods, we approximate the outer integral using Monte Carlo estimation. So what are the benefits of using policy gradient methods? Well, firstly, they generally have strong convergence properties. They can be used to learn stochastic policies, which are useful not just for exploration, but also in games, where a deterministic policy may actually yield lower returns. They also scale well for large action and state spaces, which is particularly important in multi-agent environments, where often the action spaces scale exponentially with the number of agents. Sadly, the thorn in the side of many policy gradient methods is that they often suffer from high variance, and this is what our work focuses on. Naturally, there have been a lot of research focus on techniques to reduce the variance of policy gradients. These techniques include, but are not limited to, the use of control variates, an approach which is popular in Monte Carlo methods and related works such as QProp. Another popular approach is to subtract baselines from the critic when deriving Monte Carlo score function estimators. Another question to ask is, why not just evaluate the inner integral analytically so that it does not actually contribute to the variance of the gradient? This technique is explored in my colleague's paper, Expected Policy Gradients. Another approach is to use higher order derivatives, which, as most reinforcement learning environments have action value functions that are dominated by low frequency components, we can use to derive lower variance estimators. The first two of these methods are different from, but are both compatible with the techniques developed in Fourier policy gradients. The drawback of current techniques to find analytic solutions is that they are often limited to polynomial critics, and methods that derive higher order estimators either assume a deterministic or Gaussian policy or do not consider higher than first order derivatives. So what is the contribution of our work? And how does FPG address these drawbacks? Well, firstly, we unify many existing policy gradient methods in a single, easy-to-use theorem. Our theorem provides new insights into the types of estimators that we can obtain for each parameter, giving a limit on the highest derivative with respect to action of the critic that we can use. We can also derive whole families of estimators from knowing only the characteristic function of a policy. If we prefer to use analytic solutions to the inner integral, they are readily available for several types of critic with a bound inverse Fourier transform. So let's dive into the theory of Fourier policy gradients in a little bit more detail. Firstly, we define an auxiliary policy such that the auxiliary policy is such that the reflected and shifted auxiliary policy is equivalent to the original policy. It's often convenient to shift the auxiliary policy by the mean parameter mu. For most policies, this is a natural choice, and there are various other choices for different policies. Now, substituting into the inner integral, keen-eyed members of the audience will see that this yields a convolution between the critic and the auxiliary policy, as shown here. This is where the magic of FPG comes in. Now, if we have a function and we take Fourier transforms and inverse Fourier transforms, we don't change the original function. Doing so, what we've done is we have mapped this difficult integral into a simple multiplication of two Fourier transforms, the Fourier transform of the critic and the Fourier transform of the policy, known as the characteristic function. This allows us to exploit useful properties of the Fourier transform and Fourier analysis. Let's have a look at a Gaussian policy as an extended example. The corresponding auxiliary policy for a Gaussian takes the very convenient form of a zero mean Gaussian. For mu, we now substitute into the Fourier policy gradient theorem, and we take the derivative of the characteristic function. In doing so, we obtain a single factor of I omega. For sigma, we do the same, and we obtain two factors of I omega. We can then move these factors of I omega around in the frequency domain as shown. The important part of our work, the real key to it, is that multiplying by I omega in the frequency domain is equivalent to taking a derivative in the action domain. We will see that we can therefore take up to the first order derivative of the critic for mu because we've got a single factor of I omega, and we can take up to the second order derivative for sigma because we've got two factors of I omega. So let's go ahead and do this. Now we take the inverse Fourier transform and we approximate the inner integral using Monte Carlo sampling. We then obtain the following estimators for our parameters mu and sigma. And here we go. It's important to stress again that because we only had one factor of I omega to play with for mu, we obtain estimators up to the first order action derivative of q. For sigma, we had two factors of I omega, so we could obtain estimators up to the second order action derivative of q. And this is the interesting bit. How did these relate to existing methods? Well, our zeroth order method is actually equivalent to the score function estimator of SPG with the Gaussian policy. Our first order method corresponds to stochastic value gradients, SVG 0. And our second order method is equivalent to Gaussian policy gradients, an extension of expected policy gradients. As far as I'm aware, there aren't that many methods that exploit second order derivatives for policy gradients. We see that Fourier policy gradients therefore gives a powerful tool to obtain all possible estimators for a policy. We can therefore choose an estimator that minimizes variance depending on frequency components of our Q function. We also see that if we try and take higher order derivatives, for example, the third order derivative for sigma, taking the inverse Fourier transform, we get divergent integrals. So this places a bound on the order of derivative that we can use. So what about if we don't want to use estimators and instead seek to find analytic solutions? Well, happily, Fourier policy gradients also allows us to derive analytic solutions for the inner integral for any critic that has a closed form Fourier and inverse Fourier transform. For example, consider the trigonometric critic, which is a cosine function with an offset h. We, in our paper, tested this in a very toy periodic turntable alignment experiment where the goal was to align a disk to a desired angle by rotating it about its axis. We compared our FPG solutions to OpenAI baseline implementations for DPG with a neural network critic, and as you can see by the plot, FPG learns an optimal policy much quicker than DPG. This is to be expected because of our periodic action domain. In our paper, we also developed results for mixture policies and hybrid discrete continuous policies, which we posit can be useful in multi-agent settings, where having a rich class of policies is important not just for exploration, but also for optimality. Overall, we believe that the techniques developed in our paper can be used to shape the next generation of policy gradient methods, suitable for any reasonable MDP, and that, powered by these analytic results, we can achieve zero or low variance. For more information, please find me tonight at poster number 40. Thank you.
Thanks, Matthew. We have time for a quick question from the audience. Maybe I'll ask a quick question. Is there a discrete analog for what you're doing in case that the action space or policy space are over discrete actions?
Yeah, that's a really interesting question. We were actually looking at sort of using Z transforms to do a similar thing, but it's something we haven't looked into fully yet, but I think it's an interesting research direction. Thank you.
Right, thank you very much. Let's take the speaker again. And our next speaker is Jun-Yuk Oh, and he will talk about self-imitation learning.
Hi everyone, I'm Jun, and this is a joint work with EGS, Satinder, and Hongnam. So in this work, we were interested in exploration in reinforcement learning. And we started from this motivation that not all experiences are equally important. For example, in hard exploration domains, maybe good experiences are extremely rare, then those are probably more important than the other experiences. So we hypothesized that if we properly exploit certain good experiences and try to learn more from such good experiences, that it can improve sample efficiency by indirectly improving exploration. We also found that the most popular actor-critic implementations like A2C and A3C do not have a notion of exploiting past experiences. So in this work, we proposed an actor-critic method that exploits past good experiences to verify our hypothesis. And our method is called self-imitation learning. This is an off-policy actor-critic method which can learn from past experience, and this is designed to learn to reproduce past good decisions made by the agent itself. That's why this is called self-imitation. And it doesn't require any expert demonstration, so the agent learns purely from its own experience. And this method can be easily combined with on-policy methods like A2C and proximal policy optimization. And the objective function of self-imitation learning looks like this. So at each learning iteration, we sample past state action pairs from the replay buffer with the corresponding returns. So here the return means the discounted sum of rewards until termination. And we update the policy and the value according to these sample state action pairs. So we first look at the return in the past, and we compare it to the value estimate of the learning agent. And if the return in the past is greater than the value, then we simply increase the probability of the action chosen in the past, and also update the value towards the Monte Carlo return of in the past. So otherwise, if the return is less than the value estimate, then we simply ignore those state action pairs, and we do not update the policy or the value function. So this objective function looks like an advantage actor-critic because R minus V can be viewed as some advantage estimation. But our objective only focuses on good state action pairs because it only updates according to the state action pair with positive advantage. And because state action pairs with negative advantage do not contribute to the gradient in our objective function, we found that it is natural to prioritize the samples in the replay buffer according to the clipped advantage term, which is R minus V. And this naturally samples good state action pairs more frequently than the others compared to uniform sampling from the replay buffer. And in the paper, we provided some theoretical justification by showing that our self-imitation learning objective is equivalent to lower bound soft Q learning under entropy regularized reinforcement learning framework. And this lower bound soft Q learning is presented on the right-hand side equation. It's an off-policy Q learning algorithm which updates the Q function towards the return of a behavior policy mu only when the return of the behavior policy is greater than the Q function that we are learning. And this objective can be justified when the environment is deterministic because any Monte Carlo return from any behavior policy can serve as the lower bound of the optimal Q value under deterministic dynamics. And we show that our self-imitation learning objective here is actually equivalent to the lower bound soft Q learning on the right-hand side. And more details are described in the paper. So we first evaluated our idea on Montezuma's Revenge, which is one of the hard Atari games. And this game is visualized in the left figure. So in this game, the agent has to pick up the key first in order to open the door. But even picking up the key is extremely challenging because of lots of obstacles in the middle. And the right plot shows the learning curves of two different agents. A2C is the baseline actor-critic method, and A2C plus SIR is our self-imitation learning applied to A2C agent. If you first look at the A2C baseline agent's performance, the average score is simply 0 across entire training, which means that the agent doesn't learn anything useful in this game. But if you look at the best episode reward achieved by this baseline A2C agent, as shown by the dotted line in the plot, you can see that it is slightly positive. This means that even the baseline A2C agent sometimes picked up the key using some form of random exploration, but that was not frequent enough for this on-policy A2C agent to learn a good policy to pick up the key. But on the other hand, our self-imitation learning applied to A2C can quickly learn to collect the key as soon as the agent discovers it, because self-imitation learning focuses on such rare good experiences and try to learn quickly from that. And this increases the chance of opening the door because collecting the key is the precondition of opening the door. So eventually, our method achieves much higher score in this game compared to A2C agent. So we also found that our self-imitation learning significantly improves the A2C agent across many other Atari games, including many hard exploration games. And we further compared our method to existing count-based exploration methods, and we found that our method generally outperforms existing count-based exploration methods. And this is interesting because our method still relies on random exploration. And this shows that random exploration is actually quite enough to gather useful experiences on these many hard exploration Atari games. And it is important to just exploit such rare good experiences to learn a good policy. But on the other hand, we found that our method simply fails on one of the games called Venture, and we saw that our method never receives any positive reward during entire training. So if there's no good experience, then self-imitation learning doesn't help anymore. So this shows that if the reward signal is extremely sparse, then we still need some advanced exploration method in order to discover some reward signal. So this idea of advanced exploration and our self-imitation learning are complementary to each other. And finally, we applied our self-imitation learning to proximal policy optimization for continuous control. And we found that self-imitation learning improves PPO on several Mujoko tasks. And we saw that the improvement is bigger when the reward signal is delayed. So to summarize, we proposed a very simple off-policy actocratic method, which is designed to learn quickly from past good experiences by exploiting them. And we show that this improves the actocratic method on both discrete and continuous control domains, and we saw a bigger improvement, especially on hard exploration tasks. And we also show that the main bottleneck in many existing hard exploration tasks was actually the lack of exploitation of past experiences rather than the lack of a good exploration method. And also, while exploration is very important for increasing the chance of getting reward signals, it is also important to learn enough from past good experiences to learn a good policy. And our code is available on GitHub, and you are welcome to use this code and extend this idea. Thank you.
Okay, thanks to the speaker for this interesting talk. Any question for the audience? We have time for maybe one quick question. And if not, maybe I will. Oh, there is a question. Okay.
Hi, I have a question. Isn't your gradient now biased when you clip essentially all the negative advantages?
It depends on the original objective function. If you care about the original objective of reinforcement learning, which is to maximize the discounted sum of the reward, then our gradient is not actually unbiased. It is biased towards with respect to the original reinforcement learning objective, but we presented this in the paper. We presented that our objective function on the left side is actually equivalent to the right-hand side equation, so it's unbiased with respect to this lower bound soft-skill learning objective function.
All right, let's thank the speaker again and all speakers for this session. And we continue with one more session of reinforcement learning, starting with two 20-minute talks. And the first is by Yaodong Yang. We'll talk about mean-field multi-agent reinforcement learning.
Right. It's my great honor to be here. Today I'm going to present the work of mean-field multi-agent reinforcement learning. I'm Yao Dong. This work was co-authored by other brilliant researchers from UCL and the Shanghai Jiao Tong University. So, what is multi-agent reinforcement learning? Multi-agent reinforcement learning is about study a set of autonomous agents that share a common environment. where each agent in an environment tries to accomplish its own goal by learning from interactions with other agents. So far, lots of exciting developments on the multi-agent learning have been made. For example, machines are now capable of challenging human players on playing video games, which need certain level of coordination between players. Out of the video game domain, the technique of multi-agent system is starting to make real economic impact. For instance, the multi-agent learning has been used on intelligent storage robot, which helps the warehouse management free of human labor. However, on the reinforcement learning research side, we're still limited by solving the multi-agent system with only 2 agents. How to model and study the learning problem for a population of agents are still very challenging. One main reason is that in the multi-agent system, all agents are learning adaptively at the same time, which makes the environment non-stationary anymore, and the theoretical guarantee in single-agent MDP are therefore broken. So traditional way to model the multi-agent reinforcement learning problem is to borrow the paradigm from game theory called stochastic game or Markov game. In the stochastic game paradigm, as we have more agents at each state, the reward that each agent will get and the transition probability of the next state is dependent on the joint action from all the agents. Correspondingly, the value function in stochastic game for each agent j depends on the joint policy from all agents. The analogy of optimal Q function in single-agent MDP is the Nash equilibrium in stochastic game. A Nash equilibrium is just a special joint policy where no player would like to deviate from, denoted by pi star here. It is essentially an equilibrium when no one wants to change its own policy given the other's policies. And the Nash Q value at state S is the value that is calculated with all agents following the Nash policy pi star from state S and onwards. So researchers have developed learning algorithm to find the Nash policy for the general sum stochastic game. So different from the optimal policy in single agent MDP, it is called Nash Q learning. So Nash Q learning is a straightforward learning algorithm. It defines the 2-step iterative procedures. First, it tries to solve the Nash equilibrium policy for the current stage game defined by the Qt. And then it uses the corresponding Nash value just found to update the Q function. It is proven in theory that the Nash Q operator is in fact a contraction mapping. That is to say, by iteratively applying the above 2 steps, the agent's Q function will converge to the Nash Q values in the end. However, towards modeling a population of agents, say hundreds of millions or even hundreds of thousands or even millions, Nash Q learning still have strong limits. As the reward and the transition probability state space gets exponentially large, solving the Nash equilibrium for each stage game would be infeasible, let alone considering the exploration noise and the sampling efficiency due to the increasing agent number. So in this paper, we propose to employ the mean field approximation to tackle this challenge. So the main idea is that by considering the other agents as a whole using their first moment statistics, the many-body problem can be reduced into a 2-body problem. That is, the interactions between the target agent and all the other agents can be approximated as the interaction between the target agent and the mean effect agent that is abstracted from the others. So how can we apply it on the Q learning? So we first factorize the Q function using only the pairwise local interactions. The pairwise approximation of the agent and its neighbors significantly reduce the complexity of the interactions among agents. However, it somehow still preserves the potential to model the interactions of any agent pair. So similar ideas can also be found in other machine learning domains, including variational inference, factorization machine, or learning to rank. The pairwise interaction can be further approximated by the mean field theory. So consider the agent action as a discrete categorical variable, which can be shown as a one-hot encoding vector, AK. So for each agent K in the neighborhood of agent J, we could represent agent K's action AK by the mean action value computed from all agent J's neighbors, plus some fluctuations. So basically, you expand this one hot vector equals to a mean value plus some fluctuations. With the mean field approximation, we then plug in this mean value with fluctuations into the pairwise Q function and conduct the Taylor expansion. With the remainder theorem, we have the equation with the second order term. And given the mean action A bar J, the fluctuation terms sum to 0 by definition. So the first order term can cancel out. Now we look at the second order term. From the perspective of the central agent J, the action AK in the second order remainder is chosen based on the action distribution of the neighboring agent K. Therefore, the remainder term is essentially a random variable. So in our paper, we have proved that under mild conditions on the Q function, for example, when the Q function is Lipschitz smooth, the remainder term actually acts as small fluctuations near 0, bounded by the smooth constant. So with the assumption of homogeneity and the locality on all agents within the neighborhood, the term tend to cancel each other where the agent size is large, and leading to the left term of the mean field Q value. So comparing to the original joint Q function on the left-hand side, with the mean field approximation, the pairwise interaction between agent J and each neighboring agent K are simplified as the interaction between the agent J and the virtual mean effect agent A bar J. This is abstracted from its neighborhood. So based on the above mean field Q function, we developed the mean field Q learning algorithm. Note that the updating rule looks very similar to the Nash Q learning updating rule just mentioned, with Nash value function replaced by the mean field value function. So to compute the mean field value function, obviously we need to know the policy function that each agent takes when they reach an equilibrium. We therefore create the inner loop to compute the agent's equilibrium policy. So given the Q function at time step t for all agents, the agent's policy can be modeled by a Boltzmann distribution with exploration considered. So given the function of Qt, we apply the Boltzmann policy here, and we can have the policy function for each agent. Each agent samples an action from the policies. So based on the new functions, based on the new actions, the mean effect action from the neighbors for agent J need to be readjusted. So given the new mean effect value from neighbors, the policy changes. So it then starts a new round. Given the new policy, agent sample a new action. Given all the new actions, the mean action changes. With the mean action changes, the policy changes again. So it iteratively goes on and on. And the iterating process in the inner loop keeps going on until meeting a mean field equilibrium, where each agent is acting the best response to the mean effect from its neighbors. So in our paper, we list a proposition saying that it is guaranteed that there exists such a stable policy, pi tj. So with the agent policy at equilibrium being computed from the inner loop, we can finally compute the mean field value function by taking the expectation on the Q function using the equilibrium policy just found, and update the Q function in the outer loop. To summarize, with the mean field approximation, the multi-agent problem is converted into that of solving for each agent's best response with respect to the mean action computed from its neighbors. It therefore turns the many-body problem into a two-body problem for each agent. So similar to Nash Q-learning, we can define the mean field Q-learning update rules as an operator on a Q function. And under the assumption that if each stage game has the Nash equilibrium either as a global optimum or a saddle point, the mean field Q-learning operator forms a contraction mapping. That is, if one updates his Q function by iteratively applying the mean field update rules, the mean field Q function will eventually converge to the Nash Q value. Okay, so now we move on to the experiments. So we consider 5 baselines. As there are not many plug-and-play multi-agent reinforcement learning algorithms on the market for large agent number, we include the independent learning algorithm, where each agent regards the other agents as basically part of the environment. So FMQ is a modified version of independent Q learning, which increases the Q values of the actions that frequently produced good rewards in the past. REC FMQ is a further improved version of FMQ that recursively computes the occurrence frequency to evaluate then choose actions. Finally, the MAAC stands for multi-agent actor critic, which is a variant of the famous MADDPG architecture for the discrete action space. So we first tested our algorithm in the experiment called Gaussian squeeze. So in Gaussian squeeze scenario, you have n homogeneous agents. So they try to learn and act in the environment to determine their individual actions to joint optimize the most appropriate summations. So each agent has 10 action choice from integer 0 to 9. The system objective is defined in a Gaussian way where the mean and the variance of the system are predefined but unknown to the agents. So you could think of this task as a traffic flow control program, where each agent is one traffic controller trying to send some vehicles into the main road, and the goal here is really to learn to allocate system resources efficiently, making the full use of the road while avoiding congestions. Here present the results for the Gaussian squeeze environment with 3 different numbers of agents representing 3 levels of congestions. In the smallest Gaussian squeeze setting, all models show excellent performance. But as the agent number increases, MFQ and MFAC start to show the capability of learning the effective allocation. And MFQ learns even quicker after a few iterations. So we believe this advantage is due to the awareness of other agents' actions under the mean field framework. And such mechanism could reduce the noise effect of exploratory behaviors from the other agents by taking the mean. It is also worth noting that MAAC is surprisingly inefficient in learning when the number of agents becomes large. It simply fails to handle the non-aggregated noises due to the agent's explorations. So our second experiment is on Ising model. So in statistical mechanics, the Ising model is a mathematical framework to describe the ferromagnetism. The model consists of discrete variables that represent magnetic atomic agents that can be in one of the 2 states, up or down. The spins are usually arranged in a lattice, allowing each spin to interact with the neighbors. So one beautiful property of using Ising model is that it can easily allow the identification of phase change. So when the system temperature changes, the equilibrium that the whole system would reach could be different. Or if the system temperature exceeds a certain threshold, the whole system would become chaotic. For each spin, its state is affected by both the external magnetic field, H, and the local interactions from other spins. The energy of a configuration is given by a Hamiltonian function, E. So, oops. Sorry. Okay. Ooh, present. Okay. Yeah, so the configuration probability of each spin is dependent on the energy function. It is, however, computationally challenging to compute this probability, as the nature or the number of possible spins configurations are exponentially large to enumerate. So in traditional statistical mechanics, people use mean field approximation to approximate the Hamiltonian function. However, this solution needs the explicit expression of the energy function. Here we try to solve it in a model-free way. To fit the Ising model into multi-agent reinforcement learning, we transform the Ising model into a stochastic game where each agent have a binary action space, but what is different here is that here each agent does not know the energy function explicitly, but aims to understand the environment and to find the system equilibrium by learning the Q function in a model-free way. We measure the purity of the system setting called ordered parameter, which is essentially the ratio of the difference between number of ups and downs to the total number of agents. as we compare the result from reinforcement learning with the ground truth setting that is simulated by MCMC. This figure illustrates the relationship between the order parameters at equilibrium and under different system temperatures. So basically, mean-field Q-learning converges to a similar pattern as to MCMC. So this justifies the correctness of the mean-field Q-learning on the Ising model. Critically, the mean-field Q-learning discovered the same phase change pattern as MCMC. So it happens near the temperature of 1.2. And this is also what is called Marie Curie temperature. So when we first saw this piece of result, we were very excited as this is the first work that manages to solve the Ising model via model Fourier reinforcement learning. So then we look into the mean square TD error and the order parameter at the temperature when the phase change happened. So compared to the low temperature of 0.8, where mean field Q-learning is able to find equilibrium quickly, when it comes to Curie temperature, the environment enters into phase change when the systematic stochasticity domains, resulting in a lower order parameter and a higher TD error. We then visualize the equilibrium of mean-field Q-learning and the MCMC under different temperatures, both before the Marie Curie temperature, at the Marie Curie temperature, and larger than the Curie temperature. And all the parameters of the equilibrium points from MFQ, in fact, matches MCMC's results. And the spins tend to stay aligned under a low temperature of 0.9, which is before the Curie temperature. As the temperature rises to 1.2, some spins become volatile and the patches start to form as spontaneous magnetization. After it passes the Curie temperature, the system becomes unstable and disordered due to the large thermal fluctuations, resulting in a more random pattern. So the third experiment actually comes from the idea that if we want to test the effectiveness of the multi-agent learning algorithm, why not directly put them into a battlefield for a fight, right? So we used the battle game platform called M-Agent that was released during last year's NIPS. In the battle game setting, each army consists of number of agents, say 100, that are controlled by one multi-agent algorithm. And the goal of each army is to get more reward by collaborating with teammates to destroy all the opponents. So the learning algorithm is trained by self-play, and then they put against each other and for a battle. So this is the result of winning rate after 2,000 rounds of test battles. As you can see, the mean field Q-learning largely outperforms all the corresponding baselines with over 90% winning rate over independent Q-learning and actor critic. So I conclude this talk by visualizing one battle game of mean-field Q-learning versus independent Q-learning. Here, MFQ learns the strategy of going around and besiege. The mean-field approximation obviously helped the agent develop the tactics to better understand its neighbors' interactions so that they could act in group or chase to hunt. To summarize, mean-field approximation models the dynamics of interactions in the multi-agent system and turn a problem from many-body to two-body problem. And it iteratively learns the agent's best response to the main effect from its neighbors. And we show some model-free reinforcement learning success on the Ising model and leave the proof in the main paper. Thanks.
Thank you. Is there any question from the audience? Yeah.
Thank you very much for the talk, very interesting. I have a question regarding the difference between this approach and mean field games. In mean field games, you have a statistic of the influence of all the agents in the network, even if they are far away. And here you have a statistic of local interactions. So my question is, does this statistic of local interactions also summarize the influence of agents that are far away?
So I think your question can be divided into two parts. So the first question is, what's the difference between mean field Q-learning and the mean field game, right? So mean field game is a paper, I think the best paper in ICR 2018. So I think the key difference is that in mean field game, you have a pair of equations. One is called Fock-Planck equation. One is called Hamiltonian-Jacobian-Bellman equation. So the second equation is very similar to the Bellman equation we use. But the first equation is something from our perspective, is a way to do planning. So basically, it can sort of tells you what's the distribution of your mean agent, the mean effect agent in the next step. Whereas here, in the mean field Q-learning, we don't have that step of planning. What we do is do model-free learning basically from the data itself. So we don't have that planning process. And also, that's why I think in that paper, they develop this inverse reinforcement learning to tackle this problem. Because in a model-free setting, you don't have this equation telling you, okay, in the next step, where is the majority of the agent going to be, right? So your second question is the neighborhood question. Just as the first equation we've showed, the first step you need to do is to the first step you need to do is to factorize the Q-learning into summation of local agents. And that neighborhood choice does affect the experiment. And based on our findings, it needs to be case dependent. So you can't basically put all of them into it, or you only use the nearest 4 neighbors. There is no one-shot solution for our mean field Q-learning algorithm. Yeah.
Okay, thank you.
Thanks to the speaker again. And this is our second 20-minute talk by Yang Chen Pan.
I'm Yang Chen, and this work is about applying reinforcement learning to solve partial differential equation control problems. And this is co-work with Amar Masood, Martha, Sola, Piyush, and Daniel. So first, I want to introduce the motivation. So as you know, in the classical reinforcement learning domains, like mountain car or some other domains of Mujoko, and many of them are actually modeled, the underlying dynamics is actually modeled by ordinary differential equation. But actually, there are many system dynamics can be described by partial differential equation. And we think this area is kind of under-researched, and it deserves more attention. And we find that actually conventional reinforcement learning algorithms have difficulties to solve this kind of problems, and we will introduce some challenges later. First, I want to briefly review what a PDE is. So in this screenshot, you can see there is a heated silent object. The red part indicates high temperature area, and the black part indicates low temperature area. So intuitively, the rate of change should be fastest at those extreme temperature values. For example, in the highest temperature area, the only way it can, the temperature can only be lowered because the heat will be transferred to the neighbor area. But for some intermediate temperature area, the change of rate is slower because on one side it can gain heat and on the other side it can lose heat. So as a result, we can use a partial differential equation to describe this system dynamic. So the rate of change should be proportional to the concavity of the function. So in this case, it's just a second order derivative. So I want to introduce another more complex partial differential equation, and this is our main motivation example. So the purpose of this domain is to always keep the room within the room's temperature within a comfortable range. Even though there is heat invader going through the room, but we need to keep the room comfortable very well. So the process can be described by a convection diffusion partial differential equation. Convection diffusion are two typical patterns of describing the molecule movements. So in this formula, the z is a location, so it is just a two-dimensional vector for the 2D room. So this equation is saying that the rate of change at the location z is equal to the change contributed by the diffusion process plus the change contributed by the convection process plus a source term. So the source term is usually described used to describe the change due to some natural process. In this case, it's the heat invader. So to use reinforcement learning to solve the problem, we need to first formulate it as a Markov decision process. So first, we need to redesign about the source term here. We think we can decompose the source term to two parts. One part is S superscript 0. This part is something we cannot control, like the heat invader. And another part is something we can control, which is the action. For example, we can put air conditioners on the floor, and we can control the temperature by setting the temperature of the air conditioners. So you might notice that in this MDP, both the state and action are infinite dimensional vectors, because theoretically you can measure the temperature at every point in the 2D room. And also you can also put air conditioner on every point on the 2D room. So it is both state and action are infinite dimensional vectors. And I will explain how to deal with this later. So we can intuitively design the reward term as the negative of the cost plus how far away we are from the, plus the cost incurred by how far away we are from the comfortable temperature range. It's just intuitive design. So the challenge is we have function-valued action space and with the spatial regularities to handle. So for spatial regularities, what I mean is because from the physical process itself, you can see that the temperature, if you measure the temperature at two very close points, their temperature should be very similar. And if you put air conditioners on 2 points, and the 2 points are very close, then we should also set similar temperature to the air conditioners. So in mathematical language, we can think we actually want the action function to be Lipschitz continuous with respect to the action location. So our main approach is trying to utilize this spatial regularity. We introduced the concept of an action descriptor, which is used to model the selection of action dimensions. So on the heat invader domain, and one descriptor is just a location. It's the location where you want to put the air conditioner. In implementation, it's a very easy modification. So for example, let's say, let's just use the DDPJ as an example, since it's quite popular to deal with continuous control. So in DDPG, if we want to evaluate the action function at k locations, then the output of the actor network is simply a k-dimensional vector. But with our approach, the output of the actor network is only in a single unit. And the way we get the k-dimensional action is to evaluate the function at k points, at k locations. So we will have, so when in implementation, you just need to give one more input to the actor network. But there is one question left. How can we convert it back? Because theoretically, this is infinite dimensional. How can we convert it back to arbitrary high-dimensional action? So we introduced the concept of an adapter. This is a mapping mapped from finite dimensional to infinite dimensional space. An example is we can use either Fourier diagram or design some very clever interpolation method. For the Fourier diagram, what we do is we design a partition of the space of the 2D room, and then with k subsets, and we can simply set all the action values in the same subset, just the same value. So just to make it clear, so assume we want to evaluate the action, just want to evaluate the action function at k locations, and then the box is just a subset. So what we do is once we get the action value at the Z1 location, then we can simply set the whole the action values within the whole box as the same value. So there are several possible benefits for doing this. So first, it is easy to scale to arbitrary high-dimensional action because you can just simply feed more locations into the actor network. Another benefit is it is flexible to handle dynamic action locations. So you might be maybe you can move the air conditioner. So because we expect the network should have certain level of generalization ability, so it might still give you some reasonable values. And we also think it should have a higher sample efficiency, and we provide some theoretical insight for this. So the basic idea is that we define two policy spaces, and the first one is pi subscript L, and this is assumed to be a space where each policy in this space is Lipschitz continuous with respect to the action location. And we manually design another space, pi underscore. So this space is actually used to approximate the first space. It does not explicitly capture the Lipschitz continuity, but it can provide epsilon approximation to any element in the first policy space. And we derive the polarization to describe the upper bound, the logarithm of the current number for the two policy spaces. You can see that in the first upper bound, it is an addition operation, and for the second one, it is a product. And furthermore, you can see in the second upper bound, the radius in the current number is actually a half, so we expect this number should be much larger. Actually, we provide more intuition about the meaning of the two upper bounds from the regular supervised learning setting, because in reinforcement learning, it's usually very difficult to directly say something about sample efficiency, because it's also related to exploration strategy. So this is some experimental result. This is a 2D heat equation domain. And when I introduced the intuition of PDE, I introduced a one-dimensional PDE, but this is just 2D. So you can see that the left figure has action dimension in 36, has 36 continuous action dimension, and the right figure has 256. I think this is the first result showing such large continuous control problems. So you can see that, so there are three algorithms here. DDPG is just the original version of DDPG. And DDPG with action descriptor is our approach. And DDPG with separate neural network is trying to simulate the policy search in the second policy space. It doesn't capture any relationship between the action dimensions. So what we do is we use a separate neural network for each action dimension. So you can see that when you increase the action dimension to 256, almost all algorithms decrease, but our algorithms continued improving. But the other two is kind of degrading after the 150 episode. So in this figure, it's not very clear the relative performance between DDPG and DDPG with separate neural network. Maybe because the regularity in this domain is not very strong. Let's see a more complex domain. This is a heat invader I just introduced before. And you can see that given the left-hand side is just a 25 action dimension, and the right side is 200 action dimension. So in the left side, when you only have 25 L conditioners, that from the learning curve we see that maybe the control is not fine enough. We can have more. And so when we have 200 L conditioners, our algorithm can achieve the basically optimal policy very quickly. And the other two are kind of as we expected, because we expected the DDPG with separate neural network should have lower sample efficiency. And it cannot, and it's very difficult for this algorithm to exploit the regularity between action dimensions. So next, I'm going to show you two videos during the learning process. But before that, I want to remind you the reward function and the problem setting. So the reward function is designed by two components. The cost from the action, because we use L conditioner, it costs energy. So there is a cost for the action. So, and also the cost of being out of comfortable temperature range. And there is also the fan. The fan is used to provide airflow. So you can imagine that after we turn on the air conditioner, there is sufficient airflow in the room so we can mix the air efficiently. That could lower the temperature faster. So the fan setting is not part of the action, but it is in our experiment, we set it as an environment setting. So there are two fans on the left side and right side. A fan will be triggered if the sum of absolute air conditioner temperature values is greater than some threshold. And all the air conditioners in this experiment lies in the middle part. So intuitively, an optimal policy should I want to trigger the fan definitely because I want to mix the air quickly, but I do not want to use too high absolute temperature values for the air conditioner. I want to keep the temperature, the absolute value as low as possible, but I still want to trigger the fan. That should be a near optimum policy. So this is the second episode. By using our algorithm with action descriptors, the action is in 100-dimensional. It is 100-dimensional. And I want to mention that in this figure, when we generate the video, the setting is slightly different with the learning curve I just showed you, because I want to make the visualization better. This is the second episode, and the policy is pretty poor. So what you just see is this is a room. This is a heat map for the room, for the two-dimensional room, and this figure is the reward per step. So the episode has 40 steps, and this one is the fan status at each step. So the reward is not a accumulated reward, just the reward at each time step. So let's see a better policy. This is at the 350th episode. It basically reaches converges to an optimum policy. So you can see the reward can always keep at a high level, and the fan is always on. And you do not see very strong colors in the heat map. That is what we want. And we also tried that in this setting. This setting is actually more difficult than the setting I used to generate the learning curves, because I have a higher threshold for triggering the fan. So we tested DDPG on this setting. The original DDPG basically doesn't work. So we have two possible future directions, and one is we can extend this work to classical reinforcement learning domains, because like those domains in Mujoko, although they may not have spatial regularities, but they possibly have other types of relationships. And we can also extend the work to extend this approach to work with dynamic action dimensions. So we might at each step just change the action dimension, change the number of air conditioners, and maybe also dynamically change the locations. So our poster session will be number 39. And you are very welcome to attend. I will be happy to see you there. Is there any questions?
You can start setting up. If there is a quick question, we can take it. But otherwise, we're a bit behind schedule. So let's thank the speaker again. Next is Kai-Ching Zhang, who will talk about fully decentralized multi-agent reinforcement learning.
Okay, hello everyone. Hello everyone. Today I'm going to talk about fully decentralized multi-agent reinforcement learning with network agents. First, a little bit background of the problem. So multi-agent systems has been widely used to model many practical engineering systems, including the path planning of swarm robotics and operation of distributed energy resources in smart grid. Other examples include the formation control of unmanned aerial vehicles and even in the multiplayer video games. So in order to coordinate all the agents, both centralized and decentralized protocols can be used, as shown in these two figures. And usually the latter is preferred because in many practical applications, there simply does not exist a central controller. For example, in the operation of smart grid, there is no such a controller that can control all the agents connected to the grid. And also, it is well known that this decentralized protocol has advantages of having better resilience, better scalability, and better privacy-preserving property. Another building block of work is reinforcement learning. Here, we focus on the setting that maximize the time average reward. And in this setting, one commonly used algorithm is actor critic, which enjoys advantages of both the value-based method, say Q-learning, and the policy-based method. So in particular, in the traditional actor-critic algorithm, the policy is parameterized by pi theta. And then this algorithm consists of a two-step update on different time scales. In the faster time scale, usually called the critic step, the agent does policy evaluation with function approximation. So basically, it does one step of TD learning. And then in the slower time scale, we call it an actor step. The agent update its policy parameter following this well-known policy gradient direction. And now let's jump to our model. We are basically considering the collaborative multi-agent RL problem, where the agents operate in the common environment, and each agent has its own reward function, which may correspond to different tasks that the agent is aiming to solve. And also, the evolution of the system is also affected by the joint action of all the agents. It's a very general collaborative setting. In addition, we focus on the fully decentralized setting, where we would like to develop algorithms that depends on only the information that is local to each agent, and also the control execution is also local to the agent. In particular, we consider the networked multi-agent MDP problem, where the agents are assumed to be connected by a communication network, which is possibly time-varying. And also, each agent has its own parameterized policy. But right now, the goal is to maximize the globally average return over the whole network. So this is a selected list of the related work. For the complete list, you can refer to the paper. But the main point I want to make here is that in traditional collaborative multi-agent RL, usually the reward function is assumed to be common for all the agents. Or either the other way is that they assume there exists a central controller so that the centralized critic step can be performed, as proposed in this very recent deep MLRL paper. However, we lift both of the conditions. And now let's take a look at our algorithm. So as I mentioned, that our algorithm has these desired properties, meaning that our updates are fully decentralized, and also it uses function approximation to handle the large state action spaces. And ideally, it should have a theoretical convergence guarantees under certain conditions. To do that, we first establish the policy gradient theorem for the multi-agent setting. This gives us a closed form of the globally averaged return with respect to the policy parameter of each agent. We can see that this gradient is indeed local to each agent, provided that all the agents can have a consensual estimate of this global Q or advantage function. However, this is not available to each agent. This motivates us to propose a consensus-based critic step, where we first need to develop or design a consensus weight matrix based on the this communication graph GT. And then each agent will maintain a copy of this Q function approximation. And then in the critic step, first each agent will perform a local TD update, followed by what we call the consensus update, which is basically a linear combination of all its neighbors' estimate of this parameter. Given that, each agent is able to approximate this global Q function and do a local policy gradient update. And this local policy gradient update does not depend on the update of any other agents. Also, we all know that in RL, the TD arrow unbiasedly estimates the advantage function. And this motivates us to propose the second algorithm based on the approximation of the value function. Still, each agent needs to do the local TD update followed by the consensus update. However, there's a problem because in order to evaluate this global TD arrow, each agent needs to have access to the instantaneous sample of this globally average reward, which is not available at each time t. Therefore, we propose to estimate this R bar and parameterize by R bar lambda. To do that, we need to minimize the weighted mean square error between the two. And by manipulating this objective, we can formulate it as a distributed or decentralized optimization problem with separable objective to each agent. And then we propose the decentralized SGD-based method to solve this problem. And this update are also included in the critic step. With that, each agent is able to update its parameter in a local way. And of course, our algorithm need to make sure that the step size satisfies this 2-time scale condition, which are pretty standard in the single agent actor quicker algorithm. Now let me introduce the theoretical results we have. We want to establish the convergence for this algorithm under certain conditions. So here is a list of the conditions, the list of the assumptions we have. First is the regularity conditions for the MDP, which is basically saying that given any parameterized policy pi, theta, this Markov process is ergodic. And also we need the almost sure boundedness of this reward. And also we need some assumptions on the parameter set theta, and also the vector for doing this linear function approximation, which is all standard and has been used in the literature for single agent AC algorithm. Additionally, we need some condition on the consensus weight matrix. Basically, it needs to respect the topology of this communication network, and also it needs to make sure that eventually all the agents will reach consensus. And with all these conditions, we first established the almost sure convergence of the critic step for the first algorithm. It basically shows that each agent is able to converge to the solution of this fixed point problem, which is exactly the same as the fixed point that single agent critic step converges to, although our update is fully local. And also with that, we can further establish the almost sure convergence of the actor step. Similarly, we can establish the convergence guarantees for the second algorithm. So I don't have time to go into details of the proof, but here I would like to make the following comments or remarks. Our proof framework is based on the 2-time scale stochastic approximation. Therefore, in the first step, we need to establish the convergence of the faster time scale. And for the people who are familiar with the distributed or decentralized optimization, this update may look very similar to the decentralized SGD you have. However, we all know that this TD update is not a stochastic gradient of a fixed or well-defined function. And also, because our algorithm is an online algorithm, the noises are correlated or Markovian. However, in all this literature, they assume that the noises are IID. Therefore, most of the existing proof techniques in this literature cannot be applied here. And overcoming these theoretical hurdles is non-trivial. And also, I would like to mention that as a byproduct, we have managed to show that this consensus stochastic sequence is stable, or called almost sure bounded. And in the stochastic approximation literature, this usually needs to be either assumed or proved separately. And without that, we were able to establish the same type of convergence guarantees at the single agent actor critic. So I may not have time to go into details of the simulation results, but the takeaway here is that the agents will reach consensus pretty fast in our algorithm. And then our fully decentralized algorithm will converge or achieve the same performance as the central counterpart. And this holds for the setting with linear function approximation, where we have theory about. And also, it holds in the setting with nonlinear function approximation, where we only use a very shallow neural nets for acute function approximation in a more complicated multi-agent RL task called cooperative navigation. For more details of these experiments, please check out the paper and our poster later. So to sum up, we propose a fully decentralized multi-agent RL model with network agents. And we propose the first decentralized online actor critic algorithm, which only relies on neighbor-to-neighbor communications among agents. And also, we prove the convergence of our algorithm with linear function approximation and corroborate the results via simulations. In the future, we would like to extend our analysis to the mixed setting with both collaborative and competitive agents over a network, which may involve some game theoretic analysis. And also, we are very interested in improve the almost sure asymptotic convergence of general actor critical algorithms. So finally, I would like to thank all my collaborators and fund agencies, and thanks for your attention.
Thank you. We're behind schedule, so for the interest of time, let me skip questions now and move on to the next speaker. So next is Brendan Donohue, who'll talk about the uncertainty Bellman equation. this right here. So just try to. Not the next button. Can we do slideshow here? Yeah. No, I just think that doesn't seem Hi. I'm Brendan, and this is joint work with several of my collaborators from DeepMind, Ian, Remy, and Vlad, on the uncertainty Bellman equation. And basically, the question we were trying to make progress towards answering was, how do we get an agent to explore efficiently in a reinforcement learning environment, reinforcement learning context? And we consider the case where we have an agent that is trying to estimate the Q values in an environment, kind of the usual case. And as it's estimating the Q values, it has some uncertainty about its current estimates. And we know that the Q values themselves satisfy a Bellman equation that propagates the value through time through the MDP. And in this work, we show that we can also derive a Bellman-style equation that propagates the uncertainty through time as well, through the MDP. And then we're going to use that uncertainty estimate to drive exploration in a more principled way than just something like epsilon greedy. So here's the standard Bellman equation set up. So for a given policy pi, the Q values are the unique solution to this fixed point equation, which just relates the current reward at the state in action to plus the expected kind of value from that point on to the current value. And if you could just solve this equation, you'd be done. You'd find the Q values. But in general, the expected reward at each state in action and the transition kernel, mu and p, are unknown. So the agent has to explore and gather data in order to try to understand its environment. And if we could maintain a posterior, like a Bayesian posterior over the Q values, then we could just use that to do efficient exploration. We know we can use Thompson sampling or something similar, and that has strong theoretical guarantees. But the posterior might be a very complicated distribution in general, so we can't necessarily represent it exactly. So maybe we want to approximate it, and there's lots of different approximation techniques we could do, but one thing we could try would be to appeal to the Bayesian central limit theorem, which says under some conditions you can approximate a posterior as you increase the amount of data you have with a Gaussian distribution. So if we were going to do that, we'd need the first and the second moments of the posterior. And so the first moment should be easy enough to get. You could just take the expected value of the Bellman equation. But the second moment, how do we actually get a handle on the variance of the posterior? So that's kind of the first thing we worked on in this paper, was under some assumptions we can show that the variance of the posterior of the Q value satisfies a Bellman inequality, which is given here in this slide. So this is very similar to what I had in the previous slide, which was the Bellman equation that the Q values satisfy. Here we have that the variance of the Q values of the posterior are upper bounded by, so it's not an equation, it's an inequality, something local, so some local notion of uncertainty, which kind of replaces the expected reward we had in the previous context, plus the expected value of the uncertainty of where you're going to end up, times gamma squared. If you have a discount factor, then it's gamma squared instead of gamma. So it's very similar to the Bellman equation we had before, and it kind of relates the intuitive notion that whatever, in an MDP context, whatever uncertainty I have about the Q values at my current state in action must somehow depend on some local measure of uncertainty, how well I understand the current state in action that I'm at, plus the uncertainty of where I end up. And that's what's basically captured by this inequality. And the local uncertainty we show in the paper, but you can basically just say under some assumptions it's a constant divided by the visitation count. So it goes down like
1 over the amount of times you visited that state in action. So that suggests, or it implies, that if we find a solution, if we make that inequality an equality, so we solve that Bellman equation, then those u values, which we're going to call u values, are a guaranteed upper bound on the variance of the posterior over the q values. So previously I had a Bellman inequality. If I just solve that, if I pretend it's an equation and solve it, then I get a guaranteed upper bound. We show that in the paper. And then what we can say is that, okay, we're going to approximate the posterior over the q values as a normal distribution, where the mean of the normal is just going to be the mean, say, the q bar that we solve, say, the expected Bellman equation. And then the variance is just a different Bellman equation that we can solve as well. And then we're going to use this normal approximation of the posterior to drive exploration. So you might be wondering, if you're familiar with the literature, you might know about UCB and related algorithms, which essentially take the uncertainty, take the standard deviation instead of the variance, and then add that as a bonus to the reward at each time step. And you might be wondering why we're using the variance instead of the standard deviation. Well, you can actually show that the standard deviation can come up with some poorly calibrated estimates of the uncertainty. So here's a toy problem that just illustrates that. There's an agent, it has access to 2 actions, that's it. If it takes the first action, it gets a reward. That corresponds to going to the top in this graph, in this picture. Some normally distributed reward with sigma squared variance. If it takes the second action, it gets an infinite long chain, a chain length of h of states, which has no more actions, so it just goes down this chain of states where it gets, and each reward is normal with variance sigma squared over h. And if we consider this case where the agent has taken each action n times, then the uncertainty of the first action, if you just calculate it under these assumptions, the uncertainty you have about the first action's reward is something like sigma squared over n. And the certainty you have about the second reward is also sigma squared over n, because we've chosen the sigma squared over h and this h of them, so it's sigma squared over n. So in other words, in this case, it's the uncertainty that the agent should have about each action should be the same. So you shouldn't, at least in terms of uncertainty, it shouldn't prefer one action over the other. But if you take UCB, for example, what that does, it would take the standard deviation of each state and add it as a reward bonus. So for the first action, that's fine because there's only one state, so it's sigma over root n would be the bonus. But for the second action, it compounds this standard deviation over length h. So you end up with a factor of root h too much bonus for the second action, which would mean that the agent would dramatically prefer the second action more so than it should, because in fact, we know from the previous calculation that the uncertainty estimates should be the same. And so if you actually just code this up and test it, you can show that it does learn eventually that whichever action is better, but it will take the second action way too much if in fact the first action is the superior one. Okay, so now we come to the deep RL context, and we're going to apply this uncertainty Bellman equation in order to guide exploration. And now we're firmly in the territory of heuristic, but we're going to try it anyway and see if it works. And the basic idea is you feed in the state, and that this is a very crude cartoon of a neural network. So you feed in the state into the neural network, and like, let's say you're doing DQN, you'll outcome the Q values of the estimated Q values of that particular state. But we're also going to have another output, which is the uncertainty values, the U values we're going to call them. And we're going to learn the Q values using whatever your favorite algorithm is, like DQN, and we're going to learn the U values using something like SARSA or something like that, using standard RL techniques, but using the uncertainty Bellman equation and the uncertainty reward and so on. And then as our policy, instead of using epsilon greedy, we're going to use Thompson sampling, where we combine our Q value estimate with this uncertainty value estimate and sample from it. All that's left then is to come up with what's the reward, what's the local uncertainty for our uncertainty Bellman equation. So we know in the tabular case that it's just some constant divided by the visit count, but in deep RL, we might not have access to the visit count, so there's lots of approaches you could do to try to approximate that. The way we did it in the paper, which is probably the crudest way, was to say, well, in the linear case, if you parameterize the Q values to be linear, then you can estimate the inverse pseudo counts using a particular inner product, which we have there. And then in the neural network case, we're just going to pretend it's linear and do the exact same thing. So it's a very hacky approach to getting this local uncertainty measure, but it turns out to work pretty well in practice. So we tested this on the Atari suite of games, which is 56 games. We compared against vanilla DQN, and then we compared against DQN where we add an intrinsic motivation type reward bonus, like I described earlier. This is standard deviation to the rewards. And then also compared against DQN with this uncertainty Bellman equation using Thompson sampling, as I just described, with two different approaches. One is just using a one-step SARSA update to estimate the uncertainty values, and the other one is using an n-step SARSA update to estimate the uncertainty values. And you can see that just replacing the epsilon greedy exploration, just the jittering in DQN with something a little bit more principled, which is this deeper estimates of the uncertainty, can dramatically improve the performance of this algorithm in terms of its percentage of human score and how many games it becomes superhuman in, I think this is 200 million frames. And in particular, since this is meant to be an exploration paper, we did observe that the uncertainty Bellman exploration approach did help primarily on hard exploration games. And here's what happens in Montezuma's Revenge, which is like a notoriously difficult exploration problem. Our DQN basically in 500 million frames doesn't do anything, but DQN just changing the epsilon greedy to have this slightly deeper notion of exploration and uncertainty can actually do several rooms of progress. So at scores of 3,000, that's I think 5 or 6 rooms of progress, picking up keys and opening doors and so on. So in conclusion, in this paper we derived a Bellman equation that's similar to the value propagation Bellman equation, but in this case propagates uncertainty through time. And we use the solution or an estimated solution to that Bellman equation to approximate the posterior over the values using kind of a Bayesian central limit theorem argument, and then use this approximate posterior to drive exploration. So that's it. If you have any more questions, I'm happy to talk to you at poster number 14.
Thank you very much for this nice talk. If there is a quick question, yeah.
So, can you hear me? So I'm not sure exactly where is that result, but we actually teach it in the course in the Technion where you have an exact Bellman equation for the second moments, right? So you can, like, why not use the exact same?
Okay, so there's a difference between the uncertainty, which is kind of how confident you are about your estimates of the Q values, and then the second moment of the reward distribution, which is a totally different quantity, right? Because a very random rewards, which would have a high second moment, for example, tells you nothing about how certain you are about your point estimate of the mean of the rewards, which should decrease with data. So yes, there's been a lot of work going back many decades about Bellman equations of the higher moments of the reward distribution, but not about the uncertainty that you have about your point estimate of the mean reward.
But I guess the whole, like in your work, you kind of represent that uncertainty as the second moment at the end, right? This is, yeah. So you're approximating using a Gaussian, so that's what you end up using.
Right, but we're estimating a different quantity. So in our case, the second moment should go to 0 as we get infinite data, whereas in the higher moment Bellman equations, they're fixed because they're the solution of the actual intrinsic randomness of the reward.
Okay, I see what you say. Thanks.
Sure.
All right, thank you for this talk, and I would like to thank all speakers for this session, and this concludes the session. Thank you very much.